Imagine you've spent 100 years building the most precise clock in human history. Every gear, every spring, every measurement checked and rechecked by the greatest minds alive. And then, one day, two of your clocks disagree. Not by a little, not by a rounding error, by enough to mean that everything you thought you knew about the universe, its age, its fate, its very structure, might be wrong. That's not a hypothetical. That's happening right now. And the telescope we sent into space to solve the mystery, it just made the problem worse. Here's what we know for certain. The universe is getting bigger. Every galaxy is flying away from every other galaxy, carried on the stretching fabric of space itself. We call the speed of this expansion the Hubble constant, named after astronomer Edwin Hubble, who first discovered it in 1929. For decades, measuring it seemed like just a matter of precision. Build better telescopes, gather more data, nail down the number. Except here's where it gets strange. Scientists have two ways of measuring how fast the universe is expanding, and they don't agree. The first method looks at the early universe. Using data from the Planck satellite, a spacecraft that mapped the faint afterglow of the Big Bang, physicists calculate how fast the universe should be expanding today based on known physics. Their answer, 67 kilometers per second per megaparsec. For every 3.26 million light-years between two galaxies, they're flying apart at 67 kilometers per second. The second method looks at the nearby universe. Astronomer Adam Rees and his team, known as the SH0ES team, measure real stars and exploding supernovas in galaxies relatively close to us. They use these as cosmic rulers to directly clock how fast things are moving apart right now. Their answer, 73. 6 units of difference. That might sound small, but in cosmology it's enormous. It's like measuring the speed of a bullet with two different radar guns and getting readings that are 9% apart every single time. For years, scientists said it was a measurement error. Someone's instruments were off. Someone's assumptions were wrong. They'd figure it out. But they haven't. And now one of the most powerful telescopes ever built has made the gap impossible to ignore. The James Webb Space Telescope was launched on Christmas Day 2021. With a mirror the size of a tennis court and instruments capable of detecting the heat signature of a bumblebee on the moon, Webb was designed to see further and with more clarity than anything before it. One of its first major scientific missions, independently verify the expansion rate of the universe. If Rees and the SH0ES team had made an error somewhere in their measurement chain, Webb would find it. The results came back in early 2023. Webb didn't find an error. It confirmed the higher expansion rate, 73, with even greater precision. That's when physicists started using a word they almost never use. Crisis. Not a puzzle, not an anomaly, a crisis in the standard model of cosmology, the framework that has successfully described the universe since the 1970s. So what's actually going on? Scientists have several ideas, and none of them are comfortable. The first is something called early dark energy. You've probably heard of dark energy, the mysterious force accelerating the universe's expansion. But some physicists now propose there may have been a second surge of dark energy in the very early universe, just after the Big Bang. This early dark energy could have briefly sped up expansion before fading away, leaving the universe slightly different than our models predict. Think of it like a car that accelerated hard off the starting line and then settled into cruise control. If you only watched it at cruising speed, you'd underestimate how far it had actually traveled. The second possibility is more radical: unknown physics. Some researchers suggest the laws of physics themselves, gravity, the nature of dark matter, even the behavior of light may work subtly differently across cosmic scales or different periods of time. The universe may not play by exactly the same rules everywhere, always. This is not a comfortable idea, but science doesn't care about our comfort. The third possibility is the most conservative. There's still a measurement error somewhere that nobody has found yet. The instruments are right, but the calibration is off. The math is right, but an assumption feeding it is subtly wrong. This possibility shrinks a little more every year as Webb confirms and reconfirms the higher number. But the Hubble tension isn't even Webb's strangest discovery. When astronomers pointed the telescope at the deep universe, looking back toward the first billion years after the Big Bang, they expected to see young, small, chaotic galaxies. Cosmic toddlers, still figuring out their shape. Instead, they found something that stopped researchers cold. Massive, mature, fully formed galaxies. Enormous structures that, according to our models, had no business existing that early. It's as if you dug up what you thought was an ancient campsite and found a fully built skyscraper. One astrophysicist's reaction after seeing the data went quietly viral in scientific circles. These galaxies are too old, too big, too early. They shouldn't exist. Some of this has since been partially explained. Bright, active black holes at the centers of these galaxies can make them appear larger and more massive than they actually are, inflating our estimates. Some of the mystery was a kind of telescope illusion, but not all of it. After accounting for the black holes, too many of these ancient giants remain unexplained. Our models of how gas collapses, how stars ignite, how structure builds itself up from nothing, they may be fundamentally incomplete. There's another strangeness, too. Early galaxies look odd. Instead of the familiar spiral and elliptical shapes we see in the nearby universe, many ancient galaxies appear stretched and disk-like. Some astronomers have half-jokingly described them as cosmic surfboards, pool noodles, elongated smears of light that don't match any category we expected. But here's the deeper puzzle. Some early galaxies do show spiral structure. And spiral galaxies were supposed to take billions of years to develop. They need time to flatten, to rotate, to self-organize. Seeing them fully formed so early suggests something is wrong with our timeline of how matter organizes itself. Which brings us to dark matter. Most models of galaxy formation depend heavily on dark matter, the invisible gravitational scaffolding that helps ordinary matter clump together. If dark matter doesn't behave the way our models predict, the whole timeline of cosmic structure could be off. Some physicists are beginning to ask whether dark matter is really a single, inert particle sitting quietly in the universe, or whether it's something stranger, something that interacts with itself, something that comes in different forms, or that changes over time. Any of those possibilities would change when galaxies form, how they form, and what they look like when they do. These aren't fringe ideas anymore. Webb has put them on the table. And the Hubble tension has a lesser-known companion problem called the S8 tension. S8 is a measure of how lumpy the universe is, how much matter has clumped together into galaxies and clusters versus how smoothly it's spread across space. When cosmologists use early universe data to predict how clumpy the universe should be today, and then go out and measure how clumpy it actually is, the numbers disagree again. The universe is smoother than our models predict. Matter hasn't clumped together as aggressively as it should have. This could mean dark energy is stronger than we think, or that dark matter is more slippery, or that gravity itself behaves differently on large scales than Einstein's equations suggest. Two independent cracks in the same model, and they're both growing. Now, before this starts to sound like physics is falling apart, it isn't. The standard model of cosmology is still one of the most successful scientific frameworks in human history. It accurately predicts the ratios of hydrogen and helium across the observable universe. It predicts the structure of the ancient light from the Big Bang to stunning precision. It explains the vast web of filaments and voids that connects galaxy clusters across billions of light years. It is not wrong. It is incomplete. And incompleteness is not failure, it's an invitation. In the late 1990s, astronomers noticed that distant supernovas were dimmer than expected. The universe's expansion should have been slowing down due to gravity. Instead, it was speeding up. That strange result, that crack in the data, led to one of the most profound discoveries in the history of science: dark energy. An invisible force that makes up roughly 68% of the entire universe. Something we had no idea existed until a contradiction in the numbers pointed us toward it. The Hubble tension, the galaxy formation puzzle, the S8 tension, these are the same kind of clues. Somewhere inside these contradictions is a door. And on the other side of that door may be a deeper description of reality than anything we currently have. We sent a golden telescope into the cold dark of space to answer our oldest questions. Instead, it handed us new ones. The universe is expanding faster than it should be. Ancient galaxies exist that shouldn't. Matter clusters differently than our equations predict. Dark matter, the invisible skeleton of the cosmos, may be stranger than we imagined. These are not comfortable findings, but they are honest ones. Science at its best doesn't just confirm what we hope to find, it follows the evidence even when the evidence leads somewhere unsettling. We are living in one of the rarest moments in scientific history, a moment when the data is ahead of the theory, when the universe is telling us something we don't yet have the language to hear. That's not a crisis. That's the beginning of a discovery. The James Webb Space Telescope will keep looking. Scientists will keep measuring, debating, testing, and revising. And one day, maybe 10 years from now, maybe 50, someone will look back at this exact period of confusion and contradiction and say, that was when we finally figured it out. If this video made you see the night sky a little differently, that's exactly why I make these. Drop a comment below. Which of these mysteries do you think gets solved first? The Hubble tension, the early galaxy problem, or something Webb hasn't even found yet? I want to know what you think. And if you want to go deeper, my next video covers exactly how Starship could be transformed into a massive orbital space station, why it would make the ISS look outdated, and why this concept is far closer to reality than anyone is admitting. Subscribe so you don't miss it. The universe is weirder than you think. And we're just getting started.